Okay, so looks like I'm stuck with my iPhone for a while. My DSLR just gave out. I don't know why. It just completely turns off, and I use it only to record these videos and never even leaves the tripod. It's the T6i, so it's not like the most expensive DSLR, but still, that's money out the door. Anyway, so while I wait on the replacement to come over, I'm using my iPhone. Just one more thing during this quarantine. Anyway, so what are we going to be talking about today? So today we're talking about numerical differentiation, and this is sort of the beginning of what we're doing to address a lot of the calculus concepts that we learned back in Calc 1 and Calc 2 about differentiation and integration. And so while before we had like analytic formulas, how do you take a derivative of polynomial, for instance, or how do you take a derivative of sine and cosine, or even those times each other using product rule, chain rule, etc. When it comes to actually taking differentiation of, say, a data that you get, or a function that you might not be able to write a nice clean formula for, you need to use numerical differentiation techniques. And then we're also going to learn how to do numerical integration, and we're going to have several methods for doing that. But today, we're starting out with numerical differentiation. And it's nice because it feeds, because all the stuff that we just did on interpolation and commit remainder formulas and all that stuff feeds directly into what we're going to be doing for numerical differentiation. So what we learned back in Calculus 1 is that the definition of a derivative is, say, f of x plus h minus f of x all divided by h. And as h goes to 0, if that limit exists, we say the function f is differentiable. So we can use that as sort of a 101 version of how to take a derivative numerically. So we take two different points, and we take their difference, and then we divide by h, and basically get the slope of the secant line. And then we know that if we take h to be very small, then that secant line should be roughly the same as the tangent line at the same point. So that's a nice 101 sort of way of taking a numerical derivative. But it turns out that there's better methods to do it. And in fact, if you take symmetric points around the point where you want to take the derivative, instead of taking f of x plus h minus f of x, if you say f of x plus h minus f of x minus h and divide by 2h, that actually converges a little bit faster. And we'll be able to see this sort of error formulation and see this convergence expressed through through the Newton form of the interpolating polynomials. This is something that's actually rather common that you see in numerical differentiation, numerical integration, and whatnot, is that we actually appeal back to the approximation theory that we all just learned. So, for instance, here we're using, instead of taking a derivative of f itself directly, or the data directly itself, what we do is we come up with interpolating polynomials surrounding the points that we care about, and then we take a derivative of that polynomial itself. And our intuition says that if the polynomial is really close to what the function is, then the derivative should be really close as well of the polynomial to the original function. So that's more or less the idea. And then we're going to see that rear its head again when we talk about, say, Simpson's rule for integration, where we take small intervals and then we make a little quadratic interpolation of those points in a subinterval, and then that gives us a really highly accurate method of doing numerical integration. So we're going to see these interpolating polynomials come up again and again in discussion in this class, and that's why it was a really good idea to lead with them. So in any case, so now what we're going to do is we're going to jump in and we're going to take a look at exactly how you do this using these methods. All right, so I think that's it for now, and we'll come back in a minute. Okay, so today we're going to be talking about numerical differentiation. Right, and numerical differentiation
it basically starts where where we begin. So I mean, starts where we begin. That's a great way to begin this lecture. Anyway, so we start with so we're going to let f be a function that is differentiable at a point x, and we'll say nr. Then we know that the following limit exists. Right, so it's going to be, say, limit as h goes to 0 of f of x plus h minus f of x divided by h. Right, and what we can do is we can just go ahead and say, if we want to numerically differentiate, we can take this, which is basically, we have some sort of point A, and so we have some point x, and we have some other point h, x plus h rather, and we're taking a look at the difference between these two and taking a look at their slope, right? So this is basically the secant line between these 2 points, and the idea is that when we get a really close, really small h, that's probably the worst tangent line I've ever drawn, it should get close to the tangent line if I could ever draw a tangent line. Let's start closer to the point. There we go. And so the idea is that the slope of the secant line should approach the slope of the tangent line. This is not telling you anything new. But we would like to be able to estimate f given just these sampled points. So given sampled points, say xi, yi, sometimes we'll have control of this. So 1, 2, and plus 1 if we'd like. Given sampled points, we would like to estimate f prime of x. Right. So you could just say suppose h is, say, 0.001, right? Which might be small in a certain context. Then you could just say x plus 0.001 minus f of x divided by 0.001, might be close to f prime of x, but we need to quantify. We want to quantify this. So we want to quantify the approximation. And so we want to be able to figure out what will be a good h in order to make this approximation small, and then hopefully we don't have just a big O of h, but maybe we'll have like a big O of h cubed or big O of h to the fourth, depending on how smooth f is, and so the general approach is to use interpolating polynomials. Right, and so the interpolating polynomials we're going to use are basically, basically what we know is that we have some f of x, and and if we take a look at the difference between f of x and Pn of x, where Pn interpolates these points that we talked about a second ago, that's going to give us some sort of remainder formula at each given point of x. And so we can think of f of x is Pn of x plus Rn of x. And so if we take, which then tells us that if we take f prime, if we want to guess what f prime of x is, then that's going to be Pn prime plus Rn prime of x. And so we want to demonstrate that this is small. Okay. So So let's go ahead and get into it. So using Newton's formula, what we're going to get is this. We're going to have Pn of x is equal to a naught plus a1 times n1 of x plus a2 times n2 of x plus all the way up to a n minus 1 times n sub n minus 1 of x, right? And that's going to give us a naught plus a1 of x minus x1 plus a2 times x minus x1 times x minus x2 plus all the way up to where we get a to n minus 1 of x minus x1 product until we get to x minus xn x minus 1. There we go. All right, and so that's what we're going to have. And something that we really want to take a look at is at each one of these ends. So what I'm going to demonstrate is that we can actually make a lot of these terms sort of go away when we're trying to do this sort of estimate. And so for instance, if we take a look at, say, I want to figure out what Pn prime is evaluated at, say, x1. Right, and so this involves taking derivatives of these guys, ni of x, which is going to be x minus x1 up to x minus xi. And so we're looking at the derivative of that. So if we take the derivative with respect to x, what is that going to give me? Well, it's going to be like a product rule, right? So if I had, say, x minus x1 times x minus x2, then what this is going to give me is it's going to give me say just derivative of the first, which is going to be just 1 times the second, x minus x2, plus the derivative plus the first times the second, right? And so we eliminated one of these terms. So the first time we eliminated this term and we're just left with this. And then the second time we eliminated this term and we're just left with this, right? And so when you take a derivative, you're going to basically reduce by 1 and each one of the terms, but then you have to sum over all of them. So it's going to be a sum of I going from, say, 1 up to I of the product of, say, over j not equal to I of, and that running up to, I using way too many i's here. Let's change this to k. So we're going to sum over k, and each time we're going to have all the terms except for the kth one, and we do this until we get up to I. And so this is going to be x minus xj, that product. Okay. So now here, this specifically was n2, and this here now is n2 prime, just as an example. Okay. So then you can say, well, let's see what happens if I take a look at n2 prime at x1. Well, this term vanishes, right? And so the only term that sticks around was the one, was that one. Okay, so now let's take a look and see what happens in I prime at x1. Well, so that's going to be a sum of k equals 1 to I, product of j not equaling k, running over the index. I should say that j runs not equal k, but j starts at, say, 1 and then goes up to I, right? Okay, so let's see. So we're putting in x1 in here, and the only time where x1 isn't going to show up is when j is not equal to k. And all those other times, we're going to run through this product, and we're going to end up having an x1 minus an x1, right? So that's going to give us 0. So there should only be one term that's left, and that's going to be this term, where it's going to be x1 minus x2, x1 minus x3, etc., until you get x1 minus xi. Okay? So then when we take a look at this polynomial evaluated at that particular point, what we're going to ultimately get is we get Pn prime of x1. Now the a0 was constant, so it disappears, so it's going to be 0, plus a1, and that was just multiplied by, and that was just derivative of this guy, and so that whole term disappears, plus a2, and now what is a2? Well, it is n2 prime at x1, so that's going to be x1 minus x2, plus a3 times x1 minus x2 times x1 minus x3, all the way up until we get to a n minus 1, x1 minus x2, all the way up to x1 minus xn minus 1. So really easy to write out this derivative. Okay, dumb correction here. I keep mixing up the index here. So this should actually go, we're interpolating n plus 1 points with a polynomial degree n. And so this should have actually gone up to here, n. So stop at n sub n. That's what we should be doing to get a polynomial degree n, because yeah, we're interpolating n plus 1 points, so we stop at just 1 beneath that, right? Someday I'll get this straight. I apologize for that. But yeah, in any case, continuing on. So now there are n minus 1 terms in this polynomial, and there's 2 terms in this chunk, and there's 1 term here. And so each one of these polynomials dropped from being a polynomial of degree I to a polynomial of degree I minus 1 when we did this. Okay, cool. All right, so now the big question is, who cares? What are we actually looking at here? So pulling this back, let's just take this guy with us. So the idea is that Pn prime at x1 should be close to f prime at x1. And then basically we have to remember that, say, a1 was equal to y1, y2 in our Newton form, and a2 is equal to y1, y2, y3, etc. And this is where yi is equal to f of xi, right? And etc. And so we're going to have, if we take a look at these terms here, this is where we're going to get the numerator of our quotient. So f of x plus h minus f of x is all going to come from here. So now the game is to choose good interpolation points. Say sites for estimating derivatives. Right. Okay. So why don't we go ahead and do that, and then we'll come back and talk about the remainder formula and how it's all going to play into it. So here we're going to start with 2 interpolation points. And so we're going to say we're going to have x1 and our x2 is going to be x1 plus h. Okay. So and this is for some h, say, bigger than 0. Okay, so then if we take a look at the polynomial of degree 1, that interpolates these 2 points. That's going to give us a naught plus a1 times x minus x1. And then we're left with figuring out what a naught a1 is, but then again, if we just take the derivative p1 prime and evaluated it at x1, then what we're going to be left with is just a1. Now, what is a1? Well, a1 is y1 comma y2. And that is going to be, say, y2 minus y1 divided by x2 minus x1. And then just taking a look at everything here, that tells us that p1 prime of x1 is going to be f of x1 plus h minus f of x1 divided by x2 minus x1, and that is just h. Right, so this is our sort of standard definition. Right, of our derivative. Okay, now let's see if we can figure out exactly how close we are. So how close is this? All right, well, if you take a look at the remainder formula, let me see, just pull it up real quick. So for Rn of x, with n interpolation points, it's going to be x minus x naught, x minus x1, all the way up to x minus xn, and we're taking a look at, say, the n plus first derivative of c of x over n plus 1 factorial. So c depends on x, but we'll just say c here is some point in our interval. So this is what we have, and now if we take a look at, just say, r1 of x, this and sorry, using different, this should be x1, x2 up to n plus 1. So taking a look at r1, and this is going to give us x minus x1 times x minus x2 times the second derivative of f, evaluated at some c, divided by 2. Now we don't care about r1 in particular, but we care about its derivative. And so if I take the derivative of, say, so I take a look at r1 prime of x, what we're going to end up getting is we're going to have, say, x minus x2 plus x minus x1, and this times f double prime of c over 2. And so if we want to know what is the derivative, so how close is p1 prime of x1 to f prime of x1? Well, then we take a look at, say, p1 prime of x1, subtract that from f prime of x1, and that's going to give us r1 prime of x, and that is going to give us x1 minus x2 times f double prime c over 2. And so altogether that gives us minus h of f double prime of c over 2. And if I put everything in absolute values, then we see that f prime of x minus p1 prime of x1 is equal to h times f double prime of c over 2. And in general, this tells us that f prime of x1 minus p1 prime of x1 is big O of h. And so this is sort of our approximation order. Okay, so that's a good first step. So we have demonstrated that the ordinary differentiation method ends up giving us a sort of a big O of h convergence. So it's not terrible. It's actually not great, but yeah, it converges, and so we have that going for us. Okay, so now let's take a look at another example. And so so here I'm going to take a look at these points, x1 x1 plus h and x1 minus h, right? And so this is going to be, say, our x2, and this is going to be our x3. So we're going to be looking at a polynomial of degree 2 that interpolates these 3 points. So it's going to be a quadratic. All right, so we again have a naught plus a1 times x minus x1 plus a2 times x minus x1 times x minus x2. All right, and again we have a naught is equal to, well, say y1. We have a1 is equal to, say, y1, y2 in our Newton divided differences notation, and we have a2 is equal to y1, y2, y3, right? Okay, so if I take I'm trying to estimate p2 prime evaluated at, say, x1, then that's going to give me, well, before you evaluate x1, let's just take the derivative. So it's going to be a1 plus a2 times x minus x1 plus x minus x2. And then evaluated at x1 gives me a1 plus a2 times x1 minus x2. Okay, we need to figure out what a1 and a2 are, and so we can go ahead and do that. So, so using our divided differences table, so we have our x values, which are, say, x1 plus h, x1 minus h, and then if I put y here, or sorry, say, yeah, I guess I'll just put in here. This is going to just give me, we're going to have y1, y2, and y3, and we know that each of these are just equal to themselves, so y1, y2, y3. Okay, so now let's take a look at first differences. Ultimately, this is going to be a1, this is going to be a2, and then third difference is going to be a3. And so let's go ahead and do that. So we don't care about what goes here, but we take this guy, which means we take the difference of these two guys. So we get y2 minus y1, and then we divide by the x value that's right here, and then if we go diagonal until we hit this y value, we use this x coordinate here, right? And so continuing this, we get x1 plus h minus x1, right, here on the bottom, right? And that's y2 minus y1 divided by h. Okay, now we want to do the first difference in this spot, and so that's going to be a difference between these two guys, say y3 minus y2, and now we subtract this guy from this guy, right? So we're going to have x1 minus h minus x1 plus h. Okay. All right. Now we need to figure out what goes on this spot. Well, okay, let's finish writing this out. So we have y3 minus y2 divided by, it looks like minus 2h. Okay. Now we're going to go and do our second differences. And we really only need to do it for this spot. So we're going to take a difference between this guy and this guy. So we're going to have y3 minus y2 divided by minus 2h minus y2 minus y1 divided by h, and then dividing all this guy by the x value we have all the way over here, and if we follow up diagonal until we get here, we use this x. Right, so we have x1 minus h minus x1. So let's see what we get. Well, we're going to get y3 minus y2 divided by minus 2h minus 2y2 minus 2y1 divided by 2h, and all of this divided by minus h. All right, and so continuing this, just using the space here, let's see, so we're going to have, say, a minus y3 plus a y2, and they're subtracting 2y2, so we get minus y2, and then we're going to get plus 2y1, and all of this for 2h. And then we're dividing by a minus h, so we get minus 2h squared. Whew, okay, so now let's take a look and see what this actually gives us. So we see that P2 prime at x1, so here we're going to have, say, a naught. Here we're going to have a1, and here we have a2. Okay, so now if we go through and we actually put everything in, we don't need a naught just because when we take the derivative it vanishes. So we're left with this guy. We have a1, which is going to be y2 minus y1 divided by h. And now we have plus a2, which is, say, y3 minus 2y1 plus y2, I guess, divided by 2h squared, and this times h, and that h coming from x1 minus x2. Okay, so now we can start putting everything together. I took that minus sign and I distributed it through up here, by the way. Okay, so now let's start actually putting values in for y1 and y2. And I should note that since what we're actually left with here is x1 minus x2, this should actually be minus h, right? Because x1 minus x2 is that. So that's going to give me a minus sign here instead of a plus sign. And now if I start filling in y2 and y1, well, y2 corresponds to this guy, and so that's going to give us f of x1 plus h, and then y3 is going to be f of x1 minus h, and then x1 is f of x1. So that's y1 is equal to f of x1. So we're going to start plugging that stuff in, and so what do we get? Well, we get f of, say, x1 plus h minus f of x1 divided by h, and that's this first bit, minus f of x1 minus h minus 2f of x1's, and then plus f of x1 plus h, right there, divided by 2h, because the h in power square is here. All right, now what I'm going to do is I'm going to find a common denominator, so I'm going to multiply by 2 and divide by 2 here. And when we put all that together, well, I have 2 f of x1 plus h's, and I have 1 f of x1 plus h here, so it's going to give us f of x1 plus h. And I have 2 f of x1's here that are going to cancel with 2 of f of x1's here. And so all that's going to leave us with then is we're going to have minus f of x1 minus h, and then divided by 2h. Okay, so this is my next formula. And so let's go ahead and see what happens with that. So we are looking at, say, f prime of x1, and we want to see what the difference is when I take a look at, say, f2 of x1, where I chose those particular sites. So this guy we just saw is going to be f of x1 plus h minus f of x1 minus h divided by 2h, right? And we're going to be left with some sort of remainder formula here. So we're going to ask ourselves, what is this? Well, we were talking about it before, and so R2 of x should be equal to, say, x minus x1 times x minus x2 times x minus x3 times f to the third derivative, xc, divided by 3 factorial. Okay? So if I take the derivative, r prime at x, what is this going to give me? Well, it's going to give me, say, x minus x2 times x minus x3 plus x 1, or x minus x1 times x minus x3, and it's going to give me x minus x2, or sorry, x minus x1 times x minus x2. There we go. Times the third derivative, xc, divided by 3 factorial. Put in r2 prime at x1, and what do we get? Well, we have x1 minus x2 times x1 minus x3 times f q, the third derivative, xc, divided by 6, let's say. All right, but x1 minus x2 is going to give us, so x1 was just x1, and x2 is x1 plus x2, so that's going to give us minus h. And we're going to have x1 minus x3, it's going to give us a plus h, because x3 was x1 minus h. So this is going to be minus h squared times f cubed xc divided by 6. So that tells us that f of x1 plus h minus f of x1 minus h divided by 2h is equal to f prime of x1 plus some big O term of h squared. And so this is much better. So between this one and the last one, basically we're trying to take a derivative at a point, and so the previous one basically used these points, say x and say, or x1 and x1 plus h. But it turns out that if you use this point and say this point, where this is f of x1 plus h, this one is f of x1 minus h, you get better accuracy. So using symmetry. So you get better accuracy when you're using symmetry around the point. And it's a whole order of magnitude better. And yeah, and we use the same number of samples. We used x1 and x1 plus h in the first one. Now we're just using x1 minus h and x1 plus h. But we didn't actually have to evaluate x1 in this new formula that we made up. Okay, so let's take a look at one more example, and then we can call it a day. And this is going to be this. So we're going to use these points. So we're going to use x1. We're going to use x1 plus h. We're going to use x1 plus 2h. And so this is x2 and this is x3. So again, we're using 3 points, and so we're going to have, say, p2 of x, and so it's going to be a0 plus a1 times x minus x1 plus a2 times x minus x1 times x minus x2. All right, now we just need to figure out what a naught, a1, and a2 are. So let's just go ahead and do our divided differences. So we're going to have x and say it's going to give us y's. This is going to be our divided differences. So first difference. Here. So x1, and this is going to be x2, and we'll say x3. Let's give ourselves some space here. So we'll say x1, x2, x3. And it's going to be, say, y1, y2, y3. Right? So first difference, we're going to start here. And so there's difference between y2 minus y1 divided by x2 minus x1. And so it's going to be y2 minus y1 divided by x2 minus x1 is just going to be h. Okay? And now in the next bit, it's going to be y3 minus y1, my y2, difference of these two guys. And then it's going to be x3 minus x2. So it's going to be x3 minus x2. And what does that give me? It gives me y3 minus y2 divided by h again. Okay. Now we're going to take the difference between these two guys. And so it's going to give me y2 minus y1 divided by y3 minus, divided by h minus y3 minus y2 divided by h itself, divided by, so we're going to have x3, and then we're going to divide by, subtract x1, so, and what does this give me? Well, so that's going to give me, let's see, so out of here we have y2, and we have another y2 here, and so it's going to be 2y2 minus y1 minus y3 divided by h here, and then this quantity divided by x3 minus x1 is going to be 2h. And so ultimately we have 2y2 minus y1 minus y3 divided by 2h squared. All right, and so we can put all those guys into our polynomial, and we also know that p prime of x1 is just going to be a1 plus a2 times x1 minus x2, right? Just from the last term that we had. And so putting everything into this, now a1, so this was, again, our a naught. This is our a1, and this is our, let's say this is our a2. What we get is this. So a1 is just y1 plus, oh, sorry, not y1. It is y2 minus y1 divided by h. And then we get plus our a2, which is 2y2 minus y1 minus y3 divided by 2h squared, and then this times x1 minus x2, and so x1 minus x2 is going to give me minus h. Okay, so let's take these to the next, actually we can fill this in up at the top here, so I'll switch to, say, purple. Okay, so doing everything up here, what we have now is, here this is going to be, y2 is going to give me f of x1 plus h, y3 is going to give me f of x plus 2h, and y1 is going to give me f of x1, right? So putting everything together, what we have is we have y2, which is f of x1 plus h minus y1, so it is f of x1, and then divided this guy by h, so this term here. And now I get minus 2 times f of x1 plus h minus f of x1 minus f of x1 plus 2h. And all of this divided by 2h. So I move the minus sign here, and so this should be p2 prime at x1. All right, we can do a little bit more simplification. And so I have, if I put 2's here, here, and here to give a common denominator, then what do I get? So I have 2 f of x1 plus h's, and I'm subtracting 2 f of x1 plus h's here. So that disappears. Now I have a minus 2 f of x1, and then I'm subtracting an f of x1 here, so I'm going to get, say, it's going to look at minus f of x1 total there. Then I'm subtracting subtracting negative, so it should be adding f of x1 plus 2h divided by 2h. And so altogether we get f of x1 plus 2h minus f of x1 divided by 2h. And this is another formula that we can use. You probably could have guessed that, but now let's see how accurate this is. So again, we can actually use the same exact formula. We get down to this. Since it's a quadratic, it's going to give us the same exact remainder formula. And so what's different is that we had x1, it's just x1, x2 is equal to x1 plus h, and we had x3 equal x1 plus 2h. So when I plug in everything in here, what are we going to get? Well, x1 minus x2 was minus h, and x1 minus x3 is minus 2h. So ultimately what we have is we have a 2 times h squared times the third derivative xc divided by 6. And so this gives me h squared f triple prime xc divided by 3. Now, what we can say then is that f prime at x1 is equal to f of x1 plus 2h minus f of x1 divided by, say, 2h, just like we had before, and then we can also say big O of h squared. But notice our big O constant is twice as bad as before. So because we see that we have a 3 here instead of the 6 here. So so the takeaway is that the symmetry is better. Because if we go back to that last graph, if we go back to that figure we had before, now instead of just having, say, at x1, we went 2 h's. So we went to x1 plus 2h. And by doing that, we actually got better accuracy than we had the first time round, but we got worse accuracy than if we just took symmetric points here. All right, so each of these cases, we use only 2 actual valuation points of our polynomial, but we got different accuracy each time. So let's go ahead and write down what we had. So the first one we had was f of x1 plus h minus f of x1 divided by h. And this was equal to, so this is our first estimate. So derivative estimates. So these are derivative estimators. So the first one, if we dig around enough, far enough? Okay. This is what we had. We had f double prime xc divided by 2 times h. We'll ignore the minus sign. So we had f double prime xc divided by 2 times h. So in our big O language, this is big O of h. Then we saw that we had f of x1 plus h minus f of x1 minus h divided by 2h. And this we saw is f triple prime xc divided by 6 times h squared. So this is, say, the remainder. All right, and this is big O of h squared. We'll just put everything in absolute values just so we don't have to worry about signs and everything. All right, and then we saw that if we took f of x1 plus 2h minus f of x1 and divided by 2h, again, we had f triple prime xc divided by 3 this time times h squared. And so this was also big O of h squared. And so we saw that, this is ultimately the best for the absolute error. But as far as these two match asymptotically is what we would say. So, generally speaking, big O of h squared is pretty good. This isn't a bad formula, but it turns out that you can do a little bit better if you use this formula. And that's really the takeaway here. And generally speaking, symmetry is a good thing to maintain. So in the homework, we'll see about calculating slightly higher order, maybe like using, say, 4 interpolation points, and coming up with a formula there, and you'll be able to see how your order of approximation gets here. But one thing we should note is that here, for these two guys, we have stronger assumptions. On f. So here is 3 derivatives exist. And so, whereas here, I'll only need 2 derivatives. So if you want to increase your accuracy of your method, you have to put stronger assumptions on your functions. And so here we had to assume that we actually had a function that was 3 times differentiable rather than just 2. But when we made that assumption, we got stronger results. Anyway, guys, so this is a good place to stop, and yeah, we'll jump back to the office.
Okay, so welcome back. So what we saw is that if we use the divided differences formula for integration and if we use divided differences formula for interpolation, then we can use the interpolating polynomials to come up with nice little formulas for doing numerical differentiation. We saw that using symmetric points gives you a little bit better accuracy than using the one-sided points. But sometimes you're stuck with that. Say if you have a system that starts at 1 and at say 0 and you want to take a derivative there, well, if you don't have any data behind 0, then you just have to use a one-sided. But in general, using symmetric points leads to a little bit better accuracy. So yeah, so I guess maybe I'll leave that here, and next time we'll start getting into numerical integration, and that's going to be a nice, long, and interesting topic where we talk about, say, left and right hand rules, midpoint rules, trapezoid rules, but then go into Simpson's rule and so forth. And we'll see that as we make assumptions of more and more differentiability on our functions, that we actually end up gaining better and better more and more accurate methods of integration. In any case, thank you for listening, and yeah, I'll see you next time.